Let's look at how to write electron configurations for the first period. And so here's the first period in the periodic table, and we have only two elements to worry about. We have hydrogen, and then over here we have helium. So let's start with hydrogen, atomic number of 1. So if there's atomic number of 1, that means there's 1 proton for hydrogen. In a neutral atom, the number of protons is equal to the number of electrons. So if there's 1 proton, there must be 1 electron. So our goal is to write an electron configuration for that 1 electron of hydrogen. And we're going to use the Aufbau principle. Aufbau is German for building up, because as you write electron configurations, you're thinking about the best way to build up an atom. So you're thinking about where to put your electrons. Here we have only 1 electron to worry about, so where's the best place to put the 1 electron for hydrogen? Well, we want to put that electron as close to the nucleus as possible in order to maximize the attractive force between the positive charge and the negative charge. So therefore, the electron goes into the lowest energy level possible, and that's when n is equal to 1. So we talked about quantum numbers earlier. If n is equal to 1, there's only one allowed value for L, and that's equal to 0. If L is equal to 0, there's only one allowed value for ML, right? So the magnetic quantum number, that's equal to 0. So L is equal to 0 tells us we're talking about an s orbital, and this tells us how many orientations. Only one value, so only one orientation for an s orbital. An s orbital is shaped like a sphere, right? So in this sphere, in this three-dimensional volume here, this is the most likely place, the most likely region we're going to find this 1 electron. And so the electron for hydrogen is going to go into an s orbital in the first energy level. So let's go ahead and write the electron configuration. We write the electron configuration as 1s1. Let's talk about what those mean here. So this first one, right, this is talking about the energy level, right, the shell, n is equal to 1. S says the electron for hydrogen goes into an s orbital. And this superscript 1 here, this is telling us how many electrons are in that orbital. And here, of course, we're talking about only 1 electron. So 1s1 means 1 electron in an s orbital in the first energy level. There's another way to write an electron configuration, or to draw one out. It's called orbital notation. So you draw a line here which represents an orbital. We're talking about an s orbital in the first energy level, so we could label this orbital as being the 1s orbital. And we put the 1 electron of hydrogen into that 1s orbital. And let's say the electron enters the orbital spin up. So this arrow pointing up is representing 1 electron with an up spin. So the fourth quantum number, ms, we could say that's positive 1/2 spin. So here are two ways to write the electron configuration, 1s1, or we could draw orbital notation like that for hydrogen. All right, and so we're done with hydrogen's 1 electron. Let's move on to helium now. So 2 electrons to worry about. So atomic number of 2, so 2 protons and 2 electrons. So 2 electrons to worry about. We're still in the first shell. We're still in the first energy level. So n is equal to 1. If n is equal to 1, L must be equal to 0. ML must be equal to 0. And so we're still talking about an s orbital in the first energy level, right? So we're still talking about an s orbital in the first energy level. So for helium, right, an s orbital in the first energy level like that. All right, let's think about orbital notation for helium here. So we have 2 electrons, so an s orbital in the first energy level. So we could draw the first electron for helium as spin up, right? And the second electron for helium, we would have to do that spin down. So we have to pair the spins, 1 spin up and 1 spin down. So why do we have to do that? So let me go ahead and write. I'm gonna write negative 1/2 here for the spin. The reason we have to pair the spins is because of the Pauli exclusion principle, which says that no 2 electrons in an atom can have the same 4 quantum numbers. So this first electron that we put in the 1s orbital, right? So this one right here, spin up. That would be these same 4 quantum numbers these 4 quantum numbers up here. So instead of rewriting them, I'll just circle them for hydrogen, right? And so for the second electron here, the one that I put in the orbital spin down, right, that can't have the same set of quantum numbers. So n is equal to n is equal to 1, L is equal to 0, ML is equal to 0. All those have to be the same, but the last one here, right, is different. That's why we make it -1/2, so it's spin down. And so the two electrons in helium have a different set of 4 quantum numbers, right? They differ by the last quantum number. And so that's the idea of the Pauli exclusion principle. And as a consequence of the Pauli exclusion principle, an orbital can contain a maximum of 2 electrons because you've exhausted all of the possible combinations of quantum numbers. We've used them up completely. And so the 1s orbital is completely full. So we could also write the electron configuration for helium, right, as 1s2. And once again, what that means is we're talking about an s orbital in the first energy level, and there are 2 electrons in that s orbital. So 1s2 is the electron configuration for helium. And since we have 2 electrons in the 1s orbital, we can't fit in any more electrons. And so the first shell is closed. We have a closed shell. There are no more orbitals in the first energy level. If you want to add another electron, you have to move on to the next shell. And so that takes us into the second period on the periodic table.